Okay, picture this. You're sitting on a bus, right? And you're looking out the window. Someone standing on the pavement seems to blur past you. And it kind of makes you think, wait, am I moving or is everything else moving? It's just a simple everyday thing, but it opens up this whole world of understanding motion.
It really does. And what's so interesting there is how that feeling, whether you're moving or staying still, it's not absolute. It's actually the perfect way into understanding that motion is relative.
Exactly.
And that idea, as we'll get into, it's really shaped how we see the universe.
For sure. So in this deep dive, that's what we're doing. We're going to unpack the core ideas behind motion. We'll look at all the different ways things can move, straight lines, curves, back and forth, all sorts.
And get to grips with those key concepts like rest, speed, velocity, acceleration.
Yeah.
Even something like a simple pendulum, which tells us a surprising amount.
Right. And we're drawing on some really solid educational materials here, ones that lay out these fundamentals clearly.
Yeah, think of it as sort of decoding the mechanics of movement, giving you the tools to maybe see the world around you a bit differently.
And our mission, really, especially for you, the learner listening in, is to make all this super clear, keep it engaging, and maybe, just maybe, spark some real curiosity.
Definitely. No feeling overwhelmed, just those aha moments.
Exactly. So, shall we jump into the dynamics of movement?
Let's do it. And the best place to start is probably with those basics. Rest and motion.
Okay.
And the key thing right off the bat is realizing they aren't properties of an object just by itself. It's always in relation to something else.
Right. So if something's at rest, it just means it's not shifting its position compared to its immediate surroundings. The things we decide are fixed.
Precisely. Like a book on a table or a park bench, they stay put relative to the table or the ground. They maintain that constant spatial relationship. So motion is just the opposite. An object's in motion if it is changing position over time compared to those surroundings. A bird flying, that bus we talked about, even the pendulum in a clock swinging.
They're all changing where they are relative to, say, the ground or the clock case.
Exactly.
And this is where that relativity thing gets really interesting. Back to the bus.
Yeah.
You could be sitting perfectly still compared to the person next to you, but you're definitely moving compared to the trees flashing past outside the window. It's all about your viewpoint, isn't it?
It is entirely about the frame of reference. Who's observing, and what are they considering to be stationary? That determines if something's at rest or in motion.
Wow.
And historically, that was a massive shift. Realizing motion isn't absolute. It moved us from thinking the Earth was fixed to understanding a solar system where, well, everything's constantly moving relative to everything else.
Okay, so rest and motion depend on your perspective. Got it. Now let's dig into the different kinds of motion. Our sources list quite a few, starting with translatory motion.
Yes, translatory motion. The core idea here is that every point on the object moves through the same distance in the same amount of time and in the same direction.
Oh, okay.
So if you pick any 2 points on the object, the line connecting them stays parallel to how it started. It doesn't tilt or turn.
And a key type of that is rectilinear motion.
That's right. Rectilinear is just translatory motion along a straight line.
Like a stone falling straight down. Or a car driving on a perfectly straight road. Or maybe a coin flicked across a carom board.
Exactly. Bullet from a gun, soldiers marching straight, a sprinter on a 100-meter track, all straight line movement.
Okay. And the other main type of translatory is curvilinear.
Curvilinear motion, yes. Here, every point still moves the same distance in the same time, but the path itself is curved.
So like throwing a ball in an arc. Or a car going around a bend.
Perfect examples. Javelin throw, too. And circular motion, like a satellite going around the Earth, that's really just a special case of curvilinear motion.
Right, a perfectly circular curve.
Okay.
Now, what about rotatory motion? That sounds different.
It is quite different. Rotatory motion is when an object spins or turns around a fixed axis.
So, like the blades of a fan. Or a
Okay.
spinning top. A potter's wheel?
Precisely. A merry-go-round, the Earth spinning on its axis. What makes it distinct from translatory?
Well, with rotation, different parts of the object move different distances in the same time, right? The bits further out from the center have to travel further and faster.
Exactly. The orientation of the parts is constantly changing relative to that axis, unlike in translatory motion where the whole thing moves together without internal reorientation, so to speak.
Got it. Spinning around an axis is rotatory. Okay, what about moving back and forth along the same track? Kind of. That sounds like oscillatory motion.
That's it, exactly. Oscillatory motion is that repetitive to and fro movement. It follows the same path, centered around some stable point, what we call the mean or equilibrium position.
Like the pendulum in an old grandfather clock, or a kid on a swing.
Classic examples. A piston moving in an engine cylinder, too. And importantly, oscillatory motion is a type of periodic motion. It repeats itself regularly.
Okay, regular back and forth.
Yeah.
Periodic. Now, the sources also mention vibratory motion. How's that different from oscillatory? They sound similar.
They are related. You can think of vibratory motion as a specific kind of oscillation, but it usually involves smaller, faster movements, and often there's a change in the object's shape or size as it happens.
Ah, okay. Like plucking a guitar string. It moves back and forth really fast, and you can see it sort of blurring, changing shape.
Exactly. Or the diaphragm in a speaker cone vibrating to make sound. Or even your chest expanding and contracting slightly as you breathe. Often higher frequency, sometimes involves deformation.
Okay, that clarifies it. Now, we've said periodic a few times. Let's lock that down. What makes a motion periodic?
Simple definition. It's any motion that repeats itself after a regular, predictable interval of time.
So the Earth going around the sun that takes about 365 and a quarter days every time. That's periodic.
A very clear, long-period example. But also the ticking of a clock, the regular beat of a heart, the vibrations of a tuning fork at a specific note, those are all periodic too.
Makes sense. If it has a regular rhythm, it's periodic. So the opposite must be non-periodic motion. Motion that doesn't repeat regularly.
Precisely. Non-periodic motion lacks that consistent time interval. Think of a footballer running across a field. Their path and speed are constantly changing.
Or hitting the brakes in a car. That's a definite change, not part of a regular cycle. A rolling ball slowing down.
Good examples. The motion of tides is complex, but ultimately non-periodic in its fine details. Leaves falling in the wind, lots of irregular movements out there.
Okay, so we've got these different categories, but things can get more complex, right? What if an object is doing more than one type of motion at once? That's multiple motion.
Indeed. Multiple motion is just that an object exhibiting two or more types of motion simultaneously. A great example is riding a bike.
How so?
Well, the wheels are spinning.
Rotatory motion.
Right. But the whole bike and you on it are moving forward along the road.
Translatory motion.
Ah, okay.
Exactly.
Yeah.
Our sources also give the example of drawing water from a well with a pulley.
Right, the pulley wheel turns.
You're
The
like-
bucket goes straight up or down.
Translatory, or think about a drill bit. It spins rapidly
Rotatory.
and it moves forward into the wood.
Translatory again? Okay. Multiple motion makes sense.
And there's a very common specific combination called rolling motion.
Rolling, like a ball.
Yes, rolling motion is specifically the combination of translatory motion, the center of the object moving from one place to another, and rotatory motion happening around that center at the same time. So a car tire rolling down the street, or a cylinder rolling down a ramp.
Perfect. It's that coordinated movement of the center and rotation around the center that defines rolling.
Okay. And finally, in this list of types we have random motion. Sounds like just chaos.
Pretty much. Random motion is movement with no discernible path, characterized by sudden, unpredictable changes in speed and direction.
Like trying to follow a fly buzzing around a room, or a dust speck dancing in a sunbeam.
Exactly. Or the erratic movements of players in a field sport like hockey or football. Flying a kite in gusty wind. Complete unpredictability.
Wow, okay. So from super predictable straight lines to complete randomness. That covers a lot of ways things can move. Now, what about the consistency of movement over time? That brings us to uniform and non-uniform motion.
Right. Let's start with uniform motion. The name kind of gives it away.
It suggests consistency, yeah. Our sources say it's when an object covers equal distances in equal intervals of time.
Correct. And what does that imply about its speed?
It means the speed must be constant, not changing.
Exactly. Think of a car on cruise control on a perfectly straight, flat highway. If it holds that steady speed, say 60 miles per hour, it's undergoing uniform motion.
The source example was a car doing exactly 5 kilometers every 5 minutes. Steady pace.
Right. And if you were to plot that on a distance-time graph.
It would just be a straight line, sloping upwards, showing that constant rate of covering distance.
Perfect. So logically, non-uniform motion is.
That when the speed isn't constant. When it covers unequal distances in those equal time intervals.
Precisely. Its speed is changing. It could be speeding up, slowing down, or a mix of both.
Like that same car, but now in city traffic. Stop, start, speed up, slow down. In those 5-minute intervals, it might cover 5 kilometers, then maybe only 2, then 4. It's all over the place.
Exactly. That's non-uniform. And the graph of that motion.
It wouldn't be a straight line anymore. It'd be a curve. Right. The steepness changing reflects the changing speed.
That's it. The changing slope shows the changing speed. Okay, let's shift gears a bit and look at a really important example of periodic motion, one that's taught us a lot about oscillations, the simple pendulum.
Ah, the pendulum. Yeah, you picture that weight swinging back and forth on a string. Our sources talk about an ideal one and a real one.
They do. The ideal simple pendulum is a bit theoretical. A point mass, called the bob, hanging from a perfectly massless, unstretchable string attached to a rigid support.
Which you can't really have in reality.
Right, so a real simple pendulum gets close. A small, heavy bob to minimize air resistance effects relative to its weight, a very light but strong string that doesn't stretch much, and a very stable point to hang it from.
And when you pull it aside and let go, it swings.
It swings back and forth, and we have specific terms to describe that swing.
Okay, like the rest or mean position, that's where it hangs straight down, totally still.
Correct. Let's call that position O. Then, when it swings, it reaches maximum points on either side.
The extreme positions, let's say A on one side and B on the other.
Good. Now, one complete swing, say, starting from O, going out to A, all the way across to B, and then back to O where it started. That's one full oscillation.
Okay, one full cycle. And the amplitude.
The amplitude is the maximum distance it swings away from that central mean position. So the distance from O to A or O to B. That's the amplitude.
Got it. And the time it takes to complete one full oscillation. That's the time period, usually symbol T.
Yes, the time period, T, measured in seconds. And closely related is the frequency.
Which is how many of those full oscillations happen in 1 second, measured in hertz.
Exactly. Frequency, often written as E or F, measured in hertz, which just means cycles per second. And how are T and U related?
They're inversely related, aren't they? Like, frequency is 1 divided by the time period, EL1T.
Perfect. And conversely, T equals 1E. Now, what's really fascinating and maybe a bit surprising are the factors that actually affect this time period.
Ah, this is where those laws of the simple pendulum come in. Yeah, some are weird, like the time period doesn't depend on how heavy the bob is. That feels wrong somehow.
It does seem counterintuitive, but it's true, within limits. For a given pendulum length and gravity, a heavy bob and a light bob will swing with pretty much the same time period, assuming air resistance isn't a major factor.
Wow, okay.
Same goes for the material the bob is made of: lead, iron, wood, doesn't matter for the period. And another surprising one, for small swings, the amplitude doesn't matter either.
So whether it swings out just a little bit or a bit wider, as long as it's not too wide, it takes the same amount of time to complete a swing.
Yes, that property is called isochronism, meaning same time. It's crucial for why pendulums were so useful in clocks.
That is fascinating. So mass doesn't matter, material doesn't matter, amplitude mostly doesn't matter. What does affect the time period?
Yeah.
The length of the string.
Ah, yes. The length is critical. The law of length states that the time period is directly proportional to the square root of the effective length L of the pendulum.
Square root. So if you make the string 4 times longer,
the time period only doubles. Not 4 times longer, just twice as long. Proctosquartal.
okay. And gravity, does that play a role? Like, would a pendulum swing differently on the moon?
Absolutely. The law of gravity says the time period is inversely proportional to the square root of the acceleration due to gravity. Gravity is weaker on the moon, so g is smaller.
Inverse proportion, square root. So smaller g means a longer time period. It would swing slower on the moon.
Exactly right. Troptofrepso. And when you combine the length and gravity dependence, you get that famous formula.
That's the one. It beautifully ties together the length, gravity, and the time period.
And practically, if you wanted to measure the time period accurately, the sources say you should time like lots of swings together.
Yes, that's the standard way. You'd time maybe 20 or 50 full oscillations using a stopwatch, and then divide the total time by the number of oscillations, 20 or 50.
Why do that?
It just minimizes the error from starting and stopping the watch. Any small timing mistake gets averaged out over many swings, giving you a much more precise value for the period of one swing. Makes sense. And there's a special pendulum mentioned, the seconds pendulum.
Ah, yes. A seconds pendulum is defined as one that has a time period of exactly 2 seconds.
2 seconds for a full back and forth, so 1 second to swing from one side to the other.
Precisely. Its frequency is therefore 0.5 hertz. 1 twos equals 0.5 hertz. And on Earth, its length is roughly 1 meter or 100 centimeters. They were historically important for accurate clocks.
Cool. Okay, we've really gone deep on the pendulum.
Yeah.
Moving on slightly, let's talk about describing physical quantities. This idea of scalar versus vector quantities seems fundamental.
It really is. It's a core distinction in physics. Let's start with scalars.
Okay, scalar quantities. They're the ones that just need a number, a magnitude to be fully described, like how long something is or how much mass it has.
Exactly. Length, mass, temperature, time, volume, area, energy. Even the distance something travels. They don't have a direction associated with them, just how much.
But then vector quantities, they need more information.
They do. Vector quantities require both a magnitude and a specific direction to be fully described.
Like a force. If you push something, you need to know how hard you're pushing, magnitude, and which way you're pushing, direction.
Perfect example. Force is a vector. So are things like displacement, velocity, acceleration, weight. Their direction is crucial to understanding their effect.
So saying you walk 10 meters, that's just a distance, a scalar.
Mm-hmm.
But saying you walked 10 meters east now, that's a vector. That's displacement.
Exactly. And that difference between distance and displacement is super important for analyzing motion properly.
So distance is just the total length of the pass you actually covered, like following all the twists and turns.
Yes, it's the odometer reading, if you like. It's always a positive value, a scalar. If you walk, say, 6 meters from point A to point B, and then turn and walk 8 meters from B to C.
The total distance you've walked is just 6 plus 8, which is 14 meters.
Correct. That's the distance.
But displacement, that's different.
Very different. Displacement is the shortest straight line distance between your starting point and your ending point, and it includes the direction from start to finish. It's a vector.
So in that A to B, 6 meter, then B to C, 8 meters example, if B to C was, say, at a right angle to A to B.
Then your final position C is different from your start A. The straight line distance from A to C would be, well, using Pythagoras if it's a right angle.
A square root of
That's good.
6 squared plus 8 squared, square root of 36 plus 64, square root of 100, which is 10 meters.
Exactly. Your displacement would be 10 meters in the direction straight from A to C, which is clearly not the same as the 14 meters distance you actually walk.
Oh, okay.
Huh.
Distance 14 meters, displacement 10 meters in a specific direction. Got it.
And here's a key thing. Can you travel a long distance but have zero displacement?
Ah, yes.
Yeah.
If you end up back where you started, like running one lap around a track,
Yeah.
you've covered maybe 400 meters distance,
All right.
but your start and end points are the same, so your displacement is 0.
Precisely. That distinction is vital.
Okay, distance versus displacement is clear. Now let's bring time into it to get speed and velocity.
Okay. Speed is probably the one we use most colloquially. It's defined simply as the distance traveled divided by the time taken.
Speed distance time. So it tells you how fast you're covering ground, but not which way you're going.
Exactly. Since distance is scalar, speed is also a scalar quantity, just magnitude. Units like meters per second or kilometers per hour, kilometer.
Okay, so velocity must be the vector version.
You got it. Velocity is defined as the displacement divided by the time taken.
Velocity displacement time. So it tells you how fast your position is changing and in what direction.
Correct. Because displacement is a vector, magnitude and direction. Velocity is also a vector.
So two cars could have the same speed, say 100 kilometer,
Uh-huh.
but if one is going north and the other is going south, they have different velocities.
Exactly. Same magnitude, speed, but opposite directions means opposite velocities. Or different directions means different velocities, even if speeds are identical.
Okay, speed, distance time, scalar. Velocity, displacement time, vector. Crystal clear. Right, last big concept for today, acceleration.
Acceleration. This one describes how velocity changes. It's defined as the rate of change of velocity over time.
Rate of change of velocity. Okay.
Sure.
Since velocity is a vector, speed and direction.
Acceleration can happen if your speed changes,
Speeding up or slowing down.
or if your direction changes, even if your speed stays constant.
Ah, like going around a corner at a steady speed.
Yeah.
Your velocity is changing because your direction is changing.
So you're accelerating, even though your speedometer reading might not change.
That's a really important point. So acceleration is also a vector.
Yes, it has both magnitude and direction. The formula for average acceleration A is the change in velocity divided by the time taken.
So a text final velocity, text time,
that?
t. That's the one where v is the final velocity and u is the initial velocity.
And rearranging that gives one of those standard equations of motion, right? V dollars and u plus that dollar rate.
Exactly. That equation is super useful, especially when dealing with situations where the acceleration itself is constant, what we call uniform acceleration.
Like an object falling freely under gravity, ignoring air resistance. Its velocity increases steadily. That's a classic example of uniform acceleration. Knowing that equation lets you calculate velocity at different times if you know the starting velocity and the constant acceleration.
Phew. Okay, we have covered a lot of ground here. Or maybe I should say, we've covered a lot of displacement.
Huh. Indeed. We started right back at that basic idea of rest and motion being relative.
Yeah, then we dove into all those types. Translatory, rotatory, oscillatory, vibratory. Periodic, non-periodic, multiple, rolling, random. It's quite a list.
Then the simple pendulum, with its surprisingly elegant laws, the difference between scalars and vectors, which led us to distance versus displacement.
And speed versus velocity. And finally, acceleration is the change in velocity.
It's amazing how these fairly fundamental ideas build on each other to give us a framework for describing pretty much any kind of movement you can imagine.
From the tiniest jiggle to planets orbiting stars.
Exactly.
So, for you, the learner, maybe take a moment to think about this. Where do you see these principles playing out right now? The way a car moves, sure. But what about the leaves on a tree or the vibrations from your phone?
How is motion in all its forms shaping your immediate environment? What other things that seem simple on the surface might actually be governed by these kinds of deep, interconnected physical laws?
Yeah, keep looking, keep wondering. There's a whole universe of motion out there to explore.